All right, our next topic to touch on is samples and experimental design. So, one of the things you need to be able to do is separate or identify what type of study we're actually working with, and some terminology up front. A population consists of all of the items or subjects of interest, versus a sample is just the group that is selected for study and is some smaller group, some subset of the population. In an observational study, treatments are not imposed. Investigators are either examining data for a sample of individuals, so if they already have data from their medical records or gathered some other way, that's called a retrospective study. If they follow a sample of individuals into the future and collect data, that's called a prospective study. And both are done at different times depending what's available. And they're gathering this data in order to investigate a topic of interest about the population. Usually, what's done is they do these retrospective or prospective studies to potentially set up future experiments, um, but it's a little bit simpler, easier, and cheaper sometimes to do these observational studies to gather preliminary data first. A sample survey is a type of observational study that collects data from a sample in an attempt to learn about the population from which the sample was taken. So, survey could literally be some sort of questionnaire, but when you're gathering data from a sample of individuals, that would be a sample survey. And then an experiment, which is the other kind of big half of this chapter or this topic. In an experiment, different conditions called treatments are randomly assigned and imposed on experimental units. Um, and that's kind of the big dividing line in this unit or this topic is the difference between samples and experiments. And we'll talk a little bit more about advantages. You need to know about generalizing the results of samples or observational studies. It is only appropriate to make generalizations about a population based on samples that are randomly selected. So if you're not randomly selecting, we shouldn't generalize and say something's true about the entire population. And we want those samples to be representative of the population. And the type of sample you take affects that, and how you get your data affects that. A big key is a sample is only generalizable to the population from which the sample was selected. So, for example, if I take a sample of students from Apple Valley High School, that's great, but all I can do is generalize to students at Apple Valley High School. I cannot talk about all high schoolers or even all high schoolers in District 196. You can only generalize to the group that you took your sample from. Or another way to think it, you can only generalize to the people who were available to be a part of your sample, whether you selected them or not. So, a big key difference between observational studies and experiments is that it is not possible to determine cause and effect relationships between variables you're looking at if you're using data collected from an observational study. It might be able to suggest cause and effect, or at least may help you to see possibilities, but we cannot determine, yes, this is cause and effect. On the other hand, a well designed experiment can establish evidence of those causal relationships, that some treatment is actually causing some effect to happen. When you are sampling, if an item from the population can only be selected once, this is called sampling without replacement. You are not replacing that thing or person being drawn before you take the next part of the sample. This is usually what we do when we're talking about sampling for collecting data purposes. If an item from the population can be selected more than once, this is called sampling with replacement. That would mean that you draw this, you pull this person out, you identify that it's them, but then they have the possibility of being selected again. So in terms of our different sampling methods, a simple random sample is the only one that we can abbreviate as SRS. And SRS is a sample in which every group of a given size has an equal chance of being chosen. So if you're drawing a sample of 30 people with an SRS, any combination of 30 people can be selected, and all different combinations of 30 are equally likely. A stratified random sample involves the division of the population into separate groups called strata, which you might have heard strata before when you're talking about layers of rock in geology, or the stratosphere is one of the layers of the atmosphere. And the key with those groups is that they are based on shared characteristics. We want homogeneous grouping in those groups. So that if I'm in high school and I'm going to divide everybody into separate groups, I would want everybody in those groups to be the same on some characteristic. So maybe I put everybody in the same group based on age or grade, or I put everybody in the same group based on gender, or how they get to school, or some other factor. But everybody within a group is the same on some characteristic. Then, within each group, a simple random sample is selected. So you still end up taking there's still random sampling involved, but now you are ensuring that you get some people selected from each of these different groups, and then you combine all those to make up your overall sample that you're going to collect data from. A cluster sample also involves group, but it's a little bit different. It involves the division of the population into smaller groups that are called clusters. And the key with a cluster sample is that the clusters are mixed groups, not homogeneous like stratified. They're mixed groups and hopefully mixed and representative of the characteristics of the population. So high school classes do generally not work well for this because usually you are in a class with other people who are like you by some characteristic. Often it's grade, sometimes it's based on the difficulty level of a course or previous courses taken. Elementary school classes might work a little bit better, where generally speaking, students are randomly assigned in those. But if you do have clusters that are legitimate for use of cluster sampling, we then take an SRS from those clusters, and then we collect data from all of the observations, all the people within those clusters. So they do expedite the process of sampling a little bit. If I have 8 fourth grade classes in a big elementary school, it'll be a little bit more efficient and faster if I just randomly select 3 of those 8 classes and take everybody in the class as part of my sample, instead of having to track down individual people from potentially all 8 classes if it was a simple random sample. A systematic random sample is a sampling method in which members from a population are selected according to a random starting point, and then we select at a fixed periodic interval. So this might be, we put everybody's name at Federal High School in a list by alphabetical order. We randomly pick somebody from the first 20 people on the list, and then we pick every 20th person in the list. Or if I want a mix of people of different GPAs, I could rank everybody in the school by GPA, randomly pick one of the first 15 people that are in the list, and then from that point on, pick every 15th person until I get my sample. And then a census is when you actually select all of the items or all of the subjects in a population. Census would be ideal because then you'd have all of the information. You wouldn't need to do any other fancy statistics, but often a census is very difficult, time-consuming, and expensive to actually pull off correctly. So those were kind of the valid sampling methods. You also need to be able to identify potential sources of bias and problematic sampling methods. So in general, bias occurs when certain responses are systematically favored over others. So if there's something about how you're selecting the samples or the availability of people, that's when bias is potentially a problem. Undercoverage bias is when part of the population has a reduced chance of being included in the sample. And the reason it's a problem is then your sample will typically not be representative. So for example, before cell phones, one way people did randomly select samples is to just go through the phone book. And there still was some potential undercoverage if you didn't have a telephone, but that was a much less likely occurrence. Now, there's a huge possibility of undercoverage if you're going to use a phone book because so many people only have a cell phone and that phone number isn't listed in any phone book. Non-response bias is a little bit different. In undercoverage, the one before, you have less of a chance of being selected. With non-response, we're talking about people who were already chosen for the sample, but for whatever reason, we cannot obtain their data, either because we can't get it for some reason, or they refuse to respond. So this is bias because individuals who we're not getting data for might differ from those who we can get data for in some fashion that would lead to bias. So this could be the case where if, we're mailing out information to people who were selected from the sample and they had moved and didn't leave a forwarding address, or some people just refuse to respond. If somebody is selected for a sample with a legitimate method of choosing them, but then they don't answer their phone or respond to us when we try and collect their information, that's another type of non-response. Question wording bias is when there are problems in the data gathering instrument or the process that result in response bias. So there's a couple different ways this can work. This could be questions that are too confusing. It could be questions that are not objective, questions that are leading toward a certain result. Or question wording bias also comes into people self-reporting their responses or having issues where, if a police officer is asking you a question and people change their answer because of who they're responding to and they don't want to admit that they did something wrong to a police officer, that kind of all gets lumped in under question wording bias. And so the big issue is that any non-random, or one big issue is that non-random sampling methods introduce potential for bias because they don't use chance to select the individuals. So there are two common ones that occur in the world. One is voluntary response bias, and that's when your sample is made up of people who just volunteer or chose to participate. And there's almost always something in common with the people who choose to participate that makes them different from people who don't choose to participate. And so you are not getting a representative portion of the population in your sample. The other major non-random sample issue or type of sampling is convenience sampling. That's when we choose individuals who are easiest to include, which happens often because it is easier. But the problem is, whatever reason, whatever thing, or whatever characteristic makes a certain group of people easier to get data from, that might be related to what you're sampling about, or might make that group different from the people who are harder to get information from. So one of the things beyond just sampling and bias that you need to be aware of are what are the different ways we could obtain SRSs. And there's kind of three main classifications. So first is, if you are doing one of the AP free response questions on the test and they ask you how you are going to randomize, my advice is to use the names in a hat method. I put it in quotes because it's not like an official textbook name for it. But the idea is you assign everyone or everything a number. You write those numbers on identical slips of paper and put them into a hat. Doesn't have to be a hat. Could put them into a container. Mix the numbers thoroughly so that the order you put them in the hat doesn't matter. It's not impacted. And then you draw numbers one at a time without replacement. That's key, until you get the number you're trying to choose for the sample. I advise this one if they ask you how to randomize because it's the most cut and dried, that if you hit these things that I have listed here, then you're going to be covered as far as every route they've had before. In real life, if we are going to randomize, it's probably faster, quicker, easier to use some sort of random number generator, whether it's your calculator or the website random.org or some other digital method of selecting a random sample, because you can usually do a bunch of samples really, really fast. And if it's done on a computer or device, you can often then save those results and move them somewhere else if you need to. The only catch is make sure you skip repeats. If we're supposed to be drawing without replacement, we need to skip any repeats. If the AP exam wanted to test you on how to do a random sample, that's when they would probably have you use a random number table. With a random number table, we number everyone in the population. The catch is, because we're going to be using sets of digits, you have to make sure that each person has the same number of digits. So if I have under 100 people, but more than 10 or more than 9 people, I want to make sure everybody has 2 digits. If you have 150 people, you need to make sure everybody has 3 digits. And so you might need to put zeros in front of the actual number to make sure everybody has the same number of digits. Then you would go to the random number table to select your sample. When you're working your way across, if I'm doing 2-digit numbers, I'm going to look at 2 digits at a time. I skip any numbers that are not assigned. So like if the first number in the list was 35, I would just skip it, because for this case, I'm only looking for numbers from 1 to 28. So you skip any numbers that aren't assigned, and just like with the random number generator, you also skip repeats, because we are going to draw without replacement. All right, let's talk about experiments. The experimental units in an experiment are the individuals, and individuals could be people or it could be some sort of object or animal, I guess, that are assigned treatments. When experimental units consist of people, sometimes we use the term subjects, so don't be thrown off by that. Subjects is just a more specific name when you're dealing with humans for experimental units. In an experiment, the explanatory variable, which is sometimes just called the factor, is a variable in the experiment whose levels are manipulated intentionally. This is the thing we are changing or adjusting and then trying to observe what happens. Treatments are the specific levels or combination of levels, because sometimes we have more than one factor in an experiment. The treatments are the levels or combination of levels that we're actually giving to each of the subjects. The response variable is whatever variable that is being measured after we give the treatments to the subjects or the experimental units, and we're measuring it as an outcome of whatever we're experimenting with. So the response variable is what we're measuring at the end. Confounding variables are variables we need to be aware of and try to eliminate if possible. Confounding variable is a variable that is related to the explanatory variable in some fashion, and it's influencing the response variable, but it's not the variable we're trying to measure. And so the problem is confounding variables can create a false perception of association that's not really happening. So a simple example would be if I'm doing some sort of experiment on changing the price of my ice cream, and when I go to change the price, I try a new price, and the temperature all of a sudden gets way hotter. Well, now temperature is a confounding variable because that's also going to probably influence ice cream sales. And maybe my price is also, but that relationship between the confounding variable of temperature and the one I'm trying to actually measure, which is price and sales, might create a stronger perception of what's going on than there really is. So confounding variables are kind of these variables in the background that might mess up our results and affect what we're seeing in our response variable. Another example would be if I wanted to test a new method for reviewing for tests. And so I have my 7th hour stats class use the new method. I have my 1st hour stats class use the old method. And then I say, all right, I'm going to compare the scores. Whichever class does better, it must be the method. And there's actually a couple confounding variables here. One is the students. Maybe my 7th hour class just is stronger than my 1st hour class. The other is time of day. Maybe it happens that for stats, if you take it in the morning, you do better because you're fresh and it's the start of the day. Or reverse, maybe first thing in the morning, people are more tired and they're not ready to respond and recall information. So those would be potential confounding variables in that situation. A well-designed experiment, and that's where our goal is a well-designed experiment so we can show cause and effect, should include the following things. You should have comparison of at least 2 treatment groups, one of which could be a control group. So you can have more than 2 treatment groups, and we'll talk a little bit more about control groups in a minute, but you don't have to have a control group in every experiment as long as you have comparison between multiple treatment groups. Your experiment should have random assignment, so subjects should never be allowed to choose which group they're in. That happens in an observational study, but in an experiment, we should randomly assign the treatments to the experimental units. Replication, and this is not replicating an experiment, like repeating an experiment multiple times. Within one experiment, replication means that we just need to have more than one experimental unit in each treatment group. We should be testing each treatment on multiple different people or things or experimental units. And then last, we need to have control. We should control for potential confounding variables where appropriate. The problem with confounding variables is we don't always realize that they're there. But we should do whatever we can to control any potential confounding variables. So here's kind of a little more detail on these. Comparison is important because it allows us to determine if the treatments we are testing have an actual effect. If I test 2 treatments and one shows a much bigger improvement than the other, having that comparison between them lets me know that, oh, okay, one of these treatments is doing better. Random assignment helps to balance out all the little individual differences that exist for any uncontrolled variables. And this could be confounding variables, but it could just be the individual differences among your subjects. Not all people are biologically the same. If we randomization helps balance out all the little individual differences that we can't necessarily control for. Replication ensures that the results that we're measuring are not specific to one person or even a small group of people. And if we're seeing a consistent result in a treatment group, then we should be able to generalize that to the larger group that we do our experimental groups or experimental units from. So it helps us to make sure that we can generalize. And then control, if we control for confounding variables, it ensures that the intended treatment is what we're actually measuring at the end. If we have confounding variables, like we talked about with the ice cream sales of the test scores, I wouldn't really actually know whether it's the treatment that's causing what I'm seeing or something else. So we want to control confounding variables so we're measuring only the impact caused by our treatment. And then a control group, I mentioned that earlier. A control group is a collection of experimental units that are either not given a treatment at all, so they're kind of your baseline measurement, these people aren't getting anything, or they are given a treatment of a completely inactive substance called a placebo in order to determine if the treatment of interest has an effect. So this is often done in medical trials of, yes, we can test these new medications, but then they also will have a placebo group, because there are sometimes in experiments where the placebo group shows just as much change as the other groups involved, and that's something called the placebo effect. But if that happens, then it's not the treatments at all, it's just people's expectation that, oh, I should get better because I'm taking this medication. So a control group helps to kind of monitor to see if that's happening. So a few other pieces of that are involved with experiments. A single blind experiment is when the subjects in the experiment don't know which treatment they are receiving, but members of the research team do, or it could be vice versa. So, for example, it could be a case where you're giving a medication and you're giving a placebo, and they both look exactly the same, and the research team knows which treatment each subject is getting, but they don't. The reverse could be in something like if people are trying to experiment, or if researchers are trying to experiment between two diets, then a person's going to know what they're eating. But in that case, they might not have whoever's measuring like the results. You're probably going in and recording different, body mass index and weight and water retention and some other things. Whoever's recording that data in a single blind experiment, they wouldn't know which diet the person they're measuring data from is getting. If possible, we'd rather have even a double-blind experiment. That's where neither the subjects who are in the experiment or the members of the research team who actually interact with the people throughout the experiment know which treatment each subject is getting. There is, of course, somebody overall who's monitoring the experiment who knows which subject's getting which treatment, but not the people who are directly interacting with those people. I mentioned placebos before. The placebo effect is when the experimental units have a response to a fake treatment called a placebo. And there is a measurable response happening even though no actual treatment is given. And then a placebo is just that treatment that causes no effect. It appears to be the same as all the other treatments. We use it as kind of like a baseline comparison. So we have a couple different types of experiments, kind of more specific breakdowns that you need to be aware of. A completely randomized design is when you just take your treatments and randomly assign them to all the subjects. You don't look at any closer at any characteristics, you just randomly assign among everyone. A randomized block design is when you take your experimental units and you sort them into groups called blocks so that everybody in the same block is similar for some characteristic. And often this is done maybe with age in experiments. It can be done with gender often because males and females are different physiologically. So we sort them first. Then, once you have sorted them, the treatments are randomly assigned within each block. So if I separate into male and female blocks, I randomly assign treatments equally within the male block and also within the female block. Blocking is really just another way to eliminate confounding. It helps you to separate out any natural variability that is due to the actual variable you're blocking on. So because we know there are differences between males and females, sometimes separating those helps eliminate that as a potential issue with what the data we're collecting. Randomized block design we need to be careful. That's the experimental version, but it is similar. It kind of runs parallel to a stratified random sample. You can't interchange them. Stratified random samples are only for samples. Randomized block design only for experiments. But the idea is kind of similar in those two arenas. The last kind of experiment you need to be aware of is called a matched pairs design. Now, we talk about it separately because it does have some differences, but it's really just a special case of a block design. With a matched pairs design, you take your experimental units and you arrange them in pairs so that the pairs are matched on some factor that you think might matter. And there's actually two different ways that you can do this. One is if you have your treatments randomly assigned within each pair of individuals so that one member in the pair gets one treatment, one gets the other. And then you compare the results only within those pairs. So, for example, if we were testing like a cholesterol medication, you might measure everyone's cholesterol at the beginning of the experiment and then pair people up so that they are with somebody else who has as close as possible the same cholesterol that they do at the beginning. And then we don't compare big massive groups. We just randomly assign within each pair one person to get one medication, one person to get the other, carry out the experiment, and then you look at each pair. And if consistently, the person who's getting B is showing more improvement, then that would let you know that it's that medication. The other way you can actually pair is to pair each person with themselves, kind of. Every experimental unit would get both treatments, but now you randomly assign so that half of them get one treatment first, half of them get the other treatment first. And then you can compare each person to themselves. So this has been done. There's been questions about this on the IP exam with like plots of land or like fields where the other kind of match pairs design is where every experimental unit gets both treatments. You're kind of pairing each person with themselves, but half are randomly assigned to get one treatment first. The other half are randomly assigned to get the other treatment first, and then you swap halfway through. And the reason we do that is in case it matters which treatment they get first, we would be able to monitor for that. So this might be something where, maybe you're going to test people doing some sort of test with their, like speed test with their dominant hand and their non-dominant hand. Well, everybody's different individually. I might just be less athletic than somebody else is. So we have half the people get randomly assigned so they do their dominant hand first on this test. Then they would do their non-dominant hand second. The other half of the people would do their non-dominant hand first, their dominant hand second. In case maybe it turns out that the second time you do it, you're always going to improve a little bit just because you've done the experiment before. By having half do each way first, we kind of would be able to see that in our data. Okay, so here's kind of our last bottom line, our finishing note here. Random assignment of treatments to experimental units allows researchers to conclude that some observed changes are so large as to be unlikely to have occurred by chance. And when that happens, the results are said to be statistically significant. Statistically significant differences between groups or among experimental treatment groups, that is evidence that the treatments are actually causing the effect. That's kind of what we're hoping for in an experiment, or at least what we're looking for in an experiment. If the experimental units used in an experiment are in fact representative of some larger population or group of units, then the results of the experiment can be generalized to that larger group. Random selection of experimental units gives a better chance that the units will be representative. So it's always better to randomly assign or randomly select people when we can, rather than let people just volunteer or choose who's going to be involved. The process of statistical inference, which is what we do which we did the second half of the year, attributes conclusions based on data to the distribution from which the data were collected. So that kind of goes back to that sampling thing, is when we do our inference, when we do confidence intervals and significance tests, based on data, we can attribute that to the population where we got the data from. And then finally, here's the bottom line. If a well-designed experiment with proper comparison, control, randomization, and replication shows significant differences among the treatment groups, then we can safely conclude that the treatment caused the result. And then this result should be able to be generalized to the group that the experimental units were randomly selected from in the first place. That's the bottom line with experiments.